There's all sorts of questions that we could be asked relating to our understanding of lines and planes, the way they intersect, distances between them, angles between the way that they intersect, and so on. So in this video I just want to do one example, and we'll consider the distance from a point to a plane. So a little bit of theory, I suppose, and then we'll get in and do an example. So distance from a point to a plane. So let's try and draw the kind of situation. So let's say this is our infinite plane here, and we've got a point somewhere off in space here. We want to know what's the distance from the point to the plane. So first thing is to understand that when we say that, we always mean the shortest distance, and so that means the distance from P to the plane that would be at right angles to that plane. So let's say there's a point up here, we'll call it point Q, and that's the sort of closest point. Try and represent that. So that's the closest point. So if I was to draw that there, I'd be saying that distance there, or that line connecting P to Q, would be at right angles to Q. So let's call that D. That's the distance that we're trying to find. Now, if we're given the equation of the plane, a couple of things to say straight up. One is that that line there, the vector or the line PQ, is going to be parallel to any normal vector to the plane. So if we know any normal vector to the plane, then PQ will be parallel to N, or will be in the same direction as N. Secondly, if we know the equation of the plane, then it's quite possible that we can fairly easily find the coordinates of some other point on the plane, just by, kind of working at any point that satisfies the equation. So if we can find any other point on the plane, then we could get a vector for that one there as well. So let's say the angle between those is theta. Now, looking at that triangle that I've created there, the thing that we want to find is D, but we could say that cos theta is going to be equal to its adjacent over hypotenuse, isn't it? So it's the distance that we're interested in over the magnitude of the vector PM. And so rearranging that to make D the subject, we could say, well, D is going to be equal to the magnitude of PM cos theta. Now, it'll appear like we're making this a little bit more complex, but let's actually add into that another magnitude, and that's the magnitude of a unit vector in the direction of N. Okay, because a unit vector, well, any unit vector has a magnitude of 1, doesn't it? So that's the magnitude of the unit vector. N will certainly have magnitude of 1, so multiplying by 1 doesn't make any difference. But what it does now is that this here is in the form of the dot product, isn't it? So in fact, we would say, well, that's just equal to the dot product of the vector PM and the vector unit vector N by definition of the dot product or the scalar product. Now, because in our case we want D to be a positive, we will say it's the magnitude of the dot product, okay, so that D is positive. So that we're not getting a negative distance. So that would be a way that we could find D, and as we'll see in the example, we can probably pretty easily find those two vectors, the vector PM and the unit vector N, and so therefore just taking the magnitude of that will be the distance that we're after. Now, you may also note, and you're doing well if you recognize this, but that in fact, that bit in the magnitude or in the sort of absolute value sign there, that is actually just what we call the scalar projection of PM on N. So basically we're saying, and you might remember vector projections, we've got a formula for that on our formula sheet, the vector projection of this in the direction of N which maybe more logically here is the vector projection of this vector in the direction of PQ, since PQ is the same direction as n. So the vector projection of PM in the direction of PQ is going to be this vector here. And so if we take its magnitude, then in fact we're just going to have that distance d there. So you can remember it as well as just the magnitude of the scalar projection of PM in the direction of n. So what we'll do now is grab an example and have a go at that. And here's one from exercise 5G. We'll just do part A. So this is find the distance from the point with coordinates 1, 3, 2 to the plane with vector equation r dot 7i plus 4j plus 4k equals 9. So remember what we're trying to find is a point on the plane M, this point here, such that we can get a vector PM, and also a vector normal to the plane and the unit vector of that. So remember that in the general vector equation of the plane, this is our vector n here because it's r dot n equals a dot n equals a dot n. So our vector n, so we can say let n equal 7i plus 4j plus 4k. So therefore unit vector n is just going to be 1 over the square root of, what is it, 7 squared plus 4 squared plus 4 squared times 7i plus 4j plus 4k. So let's say that's 49 plus 16 plus 16, so 49 plus 32, is that 89? Sorry, 81. Square root of 81 is 9, isn't it? So it's going to be that one there. Also, we can say in Cartesian form, because remember, to get Cartesian form we can just substitute a general vector x, y, z for r and take the dot product of those. So in Cartesian form it's just going to be 7x plus 4y plus 4z is equal to 9. And so any point which satisfies that equation will suit as a vector, as a point M. So let's let M be the point, we want it to equal 9. Okay, I'm going to let Z be 0. So let's let Z be 0, let's let X be 1, and then what does Y need to be? So 7 times, just subbing this in here, 7 times 1 is 7, 4 times 0 is 0, so this needs to be 2, doesn't it? Such that 7 plus 2 equals 9, so that would mean that Y would need to be a half. Now just, if that was a bit quick, just pause it and check for yourself that that point does satisfy. And it doesn't matter what this point is, as long as it satisfies the equation, it is suitable as a point M. So then we're going to say PM dot unit vector n is equal to the distance that we're after. In fact, let's just the distance that we're after is equal to that. So that's equal to the magnitude of, so what's PM is M minus P. So 1/2, 0. Didn't quite make my vector big enough here, did I? So there's M minus P. So P is the point with coordinates 1 and 3 and 2. That's the one given to us in the question. So that's PM is M minus P. And we're going to take the dot product of that with the vector, unit vector n, which is, so then we can take out the factor of 1/9 and say, what is it, the dot product of 0, half take away 3 is negative 5 on 2, 0 minus 2 is negative 2, so dot product of that with 7, 4, 4. And what do we get there? Magnitude of 1/9. Dot product there is going to be 0 times 7 is 0. Negative 5 on 2 times 4, what's that going to be? Negative 10. And negative 2 times 4 is going to be minus 8. So let's just finish it off up here. That's going to be the magnitude of 1/9 times negative 18. So what's that? Negative 2. So the distance there is 2 units.